So I agreed to give this talk about the seemingly nebulous pathway to infection for SARS-CoV-2. And that's largely because a lot of the details and the terminology and even some of the basic science that surrounds the transmission pathways is unnecessarily opaque. And I think because of this, it acts almost to paralyze us in everyday decision-making processes as we assess what perhaps is a risky situation for transmission and what might represent a very low risk environment. And so I'll do my best to try to clarify some of this terminology and to introduce a few of the concepts. Along the way, I'll talk about many measurements that have been made in this context of a typical classroom and what we know about transmission that may occur in a typical classroom. And in doing so, though, I must first say that our group we're atmospheric chemists. So we are not infectious disease experts. I am not a virologist. I don't actually even really know what an ACE2 receptor is as it relates to the coronavirus. I originally came into this question largely because of our interest in how air moves, both in the indoor and the outdoor environment, and how particulates specifically could be carriers for this type of virus. So as atmospheric chemists, we sort of became interested in this whole area of indoor air quality, as Judith mentioned. And specifically, about a year ago, we built this collaboration with Johnson Controls. Now, some of you are probably familiar with Johnson Controls. They're the HVAC company. So if you go to your thermostat, you'll see this nice little insignia on the thermostat. They essentially are responsible for the conduit that connects the outdoor clean air to the indoor environment that we spend so much time in. And we became interested in the general questions about what are the factors that control variability in outdoor air quality, and how does that translate to indoor air quality? And so I'm showing here the two folks in my group, or our group, Joe and Stephanie here. They are the primary folks working on this project. And in the beginning, this project was the deployment of these small air quality boxes. You might have seen these around campus that track things like particulate matter, carbon monoxide, carbon dioxide, and things along those lines. And you can see this figure in the bottom here that shows sort of this connection point between outdoor air and indoor air, and really how the building scale is something we need to be thinking about in these connection points. And this was sort of our entry. Now, of course, in February and March of this year, our entire interest in the idea of air quality took a hard pivot. And that hard pivot, of course, is thinking about transmission pathways and transmission vectors for SARS-CoV-2 in the indoor environment. And what are some of the engineering controls that could be utilized to try to mitigate that risk? So I want to start here with what we know about various modes of transmission. And there are three modes that you'll hear about throughout the literature and throughout sort of the popular press. First, you'll hear a lot about fomite transmission. This, of course, is the situation you see in this graphic where I'm coughing or sneezing on my hands and I touch my keyboard, or I touch my doorknob, or I touch some other common surface, and a susceptible comes along and touches the same doorknob or touches the same surface and then touches their face, touches their eyes, and whatnot. This type of transmission pathway, at least for me, is something that is reasonably straightforward in terms of reducing the risk, right? I know what surfaces I touch. I know appropriate hygiene that I can take to attempt to reduce this type of risk. The second mode of transmission is nominally been termed in the medical community as being droplet transmission. And this has been associated with sort of the ballistic droplets that are forcibly ejected out of your mouth during a cough or a sneeze. And in the medical community, this has taken on a specific term that this is near field transmission. And this is something that happens within sort of a 6-foot radius. And the reason for that is that a droplet of this size was originally thought to deposit to the ground before it would evaporate or equilibrate with the humidity of the room to become what we would call a droplet nuclei, small enough to be carried by the airflows in and around a room. So this is sort of an older argument that droplets would deposit sort of before they evaporate. This is one of the modes of transmission that you'll hear a lot about. The third that you'd hear about is airborne transmission. And in the medical community, that became synonymous with sort of this longer range transmission. So this is transmission that would happen outside of that 6-foot arc, right? And this became synonymous with the types of diseases like measles or tuberculosis, in which you could become infected at very large distances away from the source or the index patient. This was thought to be carried by aerosol particles and thought to be carried by particles that were smaller than 5 microns in diameter. This is essentially the reverse situation where a particle can evaporate, or at least the water content of the particle can evaporate before it deposits to the surfaces of a room and can be carried by the room circulation. So if you look at these three components here and you think about how you might mitigate the risk, they become quite different, right? And this is part of the reason this construct exists, right? If we think about how we would mitigate risk against fomites, right? We use proper hygiene. If we think about this droplet terminology that sets this 6-foot boundary, which we'll come back to a little bit about what the origin of that is. That's a close contact environment, right? We can think about not being within anyone's boundaries there. And then the third component of this airborne transmission becomes much more nebulous, because then you want to know something about how are these particulates moving in and around the environment. So one of the things that's been proposed here, and over the last 2 days, there's been a National Academies of Science virtual workshop on this specific topic, is this dichotomy that we have about droplet versus aerosol is really not founded in the way that we think about aerosols in modern science. And this is modern aerosol science, meaning like the last 50 or 60 years. And the point here is that the emission of droplets or of aerosol is a continuum, and it's a continuum in size, and it's a continuum in terms of length scales away from the source. So perhaps more practically, or I think I write here holistically, we should be thinking about this airborne transmission vector here as being more of a near field component that might be more directly about perhaps some of these droplets, these ballistic droplets that may be, if you're in a hospital setting or a dentist setting or something, that would be directly impacted on you. But from an aerosol perspective, just the concentration gradient, that you're closer to the source as opposed to being in the far field away from it. But from an atmospheric chemist perspective or an aerosol scientist perspective, this was the part of the question that became interesting to me, and it became interesting to our group, was that this dichotomy, and also the fact that you may be able to carry transmission at longer distances, makes the problem very challenging, but it also makes part of the problem dependent on aerosol physics and transport. And that is something that the atmospheric science community has thought a lot about. And that's the reason why you see a lot of atmospheric scientists working within this subfield. Okay, so I wanted to start just by showcasing a few points of the evidence for this airborne transmission beyond 6 feet, so sort of this far field component. There are many of these that you can find in the literature and the vast number of preprints that are surrounding us, or even in the popular press. This was one of the first. This came from a restaurant. And you can see this is just the top half of the restaurant. These are 6 tables in this restaurant. The index, or the infected patient, was here sitting at table A in position A1. And the folks that became infected from this dinner party are represented by all of the red circles at the adjacent tables. And so one of the things that pops up very quickly here is that folks were infected that were far beyond this normal 6-foot region. And it raised the question, how is that possible in the context of droplet transmission alone? And so if you were to look at this restaurant that's now been analyzed in multiple different ways in the context of the ventilation, you can see a couple things that are interesting here. One is that there's actually was no outside air supply for this. This was nearly stagnant airflow, or stagnant air in the region, meaning there's no input versus output. I guess I should be careful. It's not that the air is not moving in here. The air was actually recirculated in the environment, not through filtration devices, quite rapidly. So much so that the restaurant here became zoned. It's almost like there's a firewall in between each one of these zones, and that's because they have these in-room air conditioners. And the right-hand figure here shows sort of what those ventilation lines look like, where the airflow lines are. And so you can go through the literature throughout many different countries. You can go through it for our own country, and you can find numerous examples of this long-range transmission in indoor environments that are poorly ventilated. And those are some of the real key components for this. A few things that you see very limited evidence for is substantial outdoor transmission. right? There have been a handful of different cases that have been shown. These are sustained interactions outdoors in close contact. And another piece that there's very limited evidence for currently is room-to-room transmission, meaning that you would see transmission coming from one room to an adjacent room or to an adjacent room far down the hallway. Perhaps we'll see that as we start to see things like the return to college dormitories and things like that. So there's this growing evidence from the observations of where the cases come from. But I think where this positions ourselves is in a classic example that we don't know how to assess risk, right? And if we show these two cases, these two pictures here, right, we can very clearly bin these pictures based upon risk, right? We all know this right-hand position is low risk, right? We all know that this left-hand high risk, crowded bar or restaurant, this is going to be a high-risk environment for so many different reasons that I'll be talking about today. But what we don't know much about, largely because the terminology is a little bit muddled, is we don't know as much about how we should think about activities that live between these two extremes, the things that we make decisions about every single day. So that's part of the goal of this talk, is to talk a little bit about what's in the literature that can help guide us about the space that's in between the extreme high risk and the extreme low risk environment. Okay, so I wrote out here 5 questions that I think most people were starting to ask themselves in February and March of this year. If there is an airborne transmission vector, these would be like the 5 things that I would want to know the answer to, right? So I'll start. 1, I'd want to know something about what's the size and the diameter or so of aerosol particles that are being emitted during breathing, during talking, singing, yelling, coughing. And I want to know how many there were as a function of size. If I'm an aerosol physics person, I want to know something about that initial size distribution. Added to my wish list, I'd like to know how many particles contain an active virus, right? Not just is there RNA in this particle that somebody sampled, right? But is the virus viable in the actual particulate as it's moving around the room? I'd want to know how particulates of these size ranges that could carry a viable virus are distributed in the indoor environment, right? So what engineering controls can we put in such that we do not have a large amount of viable virus floating all around the environment, all around the indoor room, like we saw in that restaurant case? 4 on the list, what's the dose required for an infection to occur? Or more specifically, what's the dose response curve for SARS-CoV-2? And finally, I guess I touched on this already, what are these various intervention strategies, if they're engineering or if they're behavioral, that can be used to attempt to mitigate risk? Essentially, how do we impose these types of interventions such that we can reduce risk if we know something about these former 4? And so what I'll talk about probably over the next maybe 20 minutes here is what we know from the literature. Some of this is pre-COVID-19, some of this is post-COVID-19, about each one of these individual questions. And then what I want to do is talk about a classroom experiment where we attempt to answer some of the unknown questions about the more realistic indoor environment. And we'll try to put this all together in a risk assessment model to try to get an understanding why environments like this restaurant or the Skagit Choir led to such high attack rates or high infection probabilities compared to environments that we might have, that we might experience on a regular day basis today. Okay. So the first one here is how are respiratory aerosol actually formed? What are the physical mechanisms for this? So I'm going to take a little bit of a 30,000-foot view on a few of these topics just so we can get through them. If anyone is interested in the nitty-gritty details about this, like I said, the National Academy of Sciences just led a virtual symposium on this. That recording will come out next week. It's about 2 days of talks on all of these types of things. I've condensed this into 60 minutes or so for you, or 45 minutes. We'll see how long we can go. So where are these particulates formed from? The smallest particles, and those that probably carry the highest viral load per unit volume, are formed through fluid film rupture that happens deep within the lungs. And those particulates are efficiently expelled from the infected individual and launched into the airways. Those may be particulates that could be on the order, at least when they're ventilated out of the mic, might be on the order of a micron or so, or smaller. The second is the vibrations that happen actually when we're talking, right? If I were to continue to talk like this at my computer screen, like all of us do, right? We end up coating our computer screen with all of the particulates and droplets that we make, right? And that happens due to some of the vibrations that we have. And then finally, some of the very large particles, or some of the droplets, right? They actually come from articulation that happens during speech, right? If we're singing, right, or if we're yelling, you can have very large droplets that are formed that are ejected from that pathway, right? You can even see it when you're singing. Like many of us has probably watched maybe the recording of Hamilton, right? You can actually see the particulates coming out as they're singing. These are the largest particles, and these are particles that may carry, it's expected, maybe the lowest viral load because they're coming from saliva that may be less dense in terms of the number of viruses per milliliter. Okay, so how do we know some of these things, or how would we actually measure the concentration of particulates that are in exhaled breath? This is something that's been done for multiple years. Essentially, you see this, guide your eyes to the schematic that's right in the center of the screen here. It's essentially taking an individual and placing them within a laminar flow hood to try to get the background concentration of aerosols around them down to 0, because we inhale a lot of particles and then we exhale them back out. So there's a baseline or background question that needs to be addressed here. And essentially, the idea is to speak into a particle counting type instrument. This is one that's utilized quite commonly because it overlaps with the size range of particulates that we're most expected to see. This essentially is a time of flight type instrument. As the particulate gets accelerated out of a nozzle, we measure essentially the time that it takes for it to traverse between 2 laser beams, and that we can deduce the aerodynamic diameter from. So experiments are done where, for example, a participant will say specific types of sounds and articulate those sounds, and the number of particulates and the size of those particulates will be measured through that process. And so what do you find from this is a classic size distribution. This is from Johnson et al. 2011. This is the size distribution of aerosol particles that are formed from speaking. It's thought that this is a bimodal size distribution because of the source of those particles being different between different parts of your respiratory system, right? As whether or not their origin is very, very low down, or whether or not it's in larynx or higher. What you find is that the size of the particles is on the order of about maybe 1 to 5 microns in diameter. You see a tail that spreads all the way out toward 50 microns in diameter. One of the things that's important here, of course, is that the particles are expelled from your mouth nearly at or almost supersaturated with respect to the water vapor. And so they quickly desiccate to the relative humidity of the room. So for example, a 10 micron particle that comes out of your mouth may equilibrate to a 3 or 4 micron size particle. This is a key little nuance to why the mask efficiency for exhalation is actually quite better than the mask efficiency for inhalation, because there's a size difference between the particulates that you're sending out of your mouth and those that you're going to inhale after they've equilibrated. So the thing that's of course interesting about this is that this necessitates that there is no real such thing as a naked virus just floating around in the air, right? So the coronavirus here is in the order of 100 nanometers, 120 nanometers or so in size. So it's being ejected out into the atmosphere here at an order a micron or several more than that. So most of the residual of that particulate is going to be salts or proteins or things like that that may carry this virus as part of its payload. How many particles here are emitted, and how does that depend on the activity? I would say this is one of the most interesting questions that's currently being looked at. Is the number of particles emitted depends strongly on whether you're breathing, talking, singing, coughing, and unfortunately even who you are, right? People articulate words in different ways. People are louder or softer than others. So this provides an opportunity to see large scale differences in particle emission based upon activity and also based upon individuals. One thing that's really interesting here is that prior study that I had shown required the participants to speak into the microphone at different levels of loudness, and essentially had the microphone to be able to track the decibels, right, of your speaking volume, and found a correlation there between the number of particles emitted and how loud you were talking. Most recently, Bill Ristenpart from UC Davis made a really strong statement here at the National Academies meeting that a 6 decibel reduction in speaking volume, which really isn't that much, can cut particle emission in half. And so we think about this even as an engineering control, right? You think about the loud bar, right? Or you think about, you know, the folks that are not using a microphone in their classroom, right? This is a pretty sizable control strategy, even when you compare it against mask efficiency. So in terms of quantitative numbers, this is, of course, where everything starts to collapse. These are the numbers that folks really want to know. Unfortunately, there still is a range on these numbers, but this is the ballpark. These are the numbers that you might want to think about. Breathing, it could be on the order of 10 particles per second. Speaking softly, maybe an order of magnitude larger, loudly another order of magnitude. Coughing can, of course, be this violent storm that injects large numbers of particles out into the atmosphere itself. That's shown here on the left-hand side too. So this is sort of the ballpark numbers that, and one of the challenges, I think, in trying to generalize this problem out in terms of risk. But we'll come back to some strategies to get around that. Okay, so one of the last questions here that comes up is what fraction of emitted aerosol particles contain a virus, right? Okay, and this is kind of like the white whale, right? This is the question everyone wants to know. And this is a really hard thing to get after, right? You can imagine those that are interested in chemical instrumentation, how you would access this question, right? How would you measure a virus in an individual particulate as it's being exhaled? Folks are thinking about that, of course. If you did something that's back of the envelope, right? If you just said, let's assume that respiratory aerosol particles, that the viruses that are in those particulates are statistically distributed based upon what they might be in mucus, right? And maybe I take a viral load that's somewhere from 10 to the 6, 10 to the 8, depending on where you are in the system. Of course, is going to vary if you're asymptomatic or symptomatic or whatnot. And if you take all that information together and you speak, you know, this could be somewhere on the order of 0 to 20 viruses per second with a lot of variability, right? And that's kind of the number that you might want to be looking at. It was recently said that if you were to articulate loudly the phrase "hello world," that you would be emitting about 25 particles or 30 particles during that phrase. Okay, so if we take this sort of expectation, the reason why I'm spending a little time on this is that because of just even the statistics of this, it leads us to expect that the virus is going to be carried in particles that are probably on the slightly larger side of this spectrum, right? It's going to be statistically challenging to find them in a 500 nanometer particle, but to find them in a 1 micron or into a 2 micron or 5 micron is likely where you're going to see them. And this comes back to when we start thinking about how effective masks are for exhalation or inhalation. Okay. The last question, okay, so we get a virus that's in a particle. Is it still viable? This has been a question that's been on the table, I think, since the beginning of the pandemic. And there are two places in which the literature has attempted to answer this question. The first is sort of what has been termed maybe as a smoking gun, is to say, well, can you actually measure viable virus in the air at a range that's larger than, say, 6 feet. And this was just recently reported, probably about a month ago, was the measure of viable virus that was collected in a hospital room at a distance that could be as large as even 5 meters away from the index patient. One of the things that's interesting about this, of course, is that index, of course, is not wearing a mask. And they, of course, are sick enough to be in a hospital room. But a hospital room also has very good ventilation, and it has very good filtration. The second question that's parallel to this is, once you launch that, is the virus going to be viable in its little payload aerosol particle for a minute, 5 minutes, an hour, or even longer? So studies have been looked at this, where essentially they take, they nebulize the virus and put it into a rotating drum, and allow that aerosol to essentially live in this rotating drum and extract out virus from that at different time constants and measure the viability of the virus. It's found that the half-life was about an hour in the aerosol, but after even like 16 hours, they were still able to see some viable virus. So these are places that there's still very active research. Okay, the last piece that is going to lead into the actual discussion of some of the measurements that we've made is how far can a respiratory aerosol particle travel? And there's been a conversation in the popular press that it can't go past 6 feet. And this is a newspaper article that was from 1918. This is from the California Aggie newspaper about an experiment that was done at Harvard, of course, during one of the former pandemics here, 1918. The experiment was pretty straightforward. You can read through the details here as you may already be, but you can imagine what type of experiment might be done 100 or so years ago, essentially to be putting the equivalent of maybe Petri dishes away from an infected individual and seeing how far out you could culture that virus. Essentially, what was found is that the bowls were infected for 10 feet at least, out to 12 feet during a cough or a sneeze, right? So this idea, of longer range transport, dates back 100 years ago. I like the end of this moral, wear your mask, 1918. So in modern aerosol physics, right? Of course, we probably wouldn't do just the Petri dishes, but we could actually calculate out a few things about it. Okay, so the simplest thing that you would do if you wanted to calculate out how long a particle is going to live in a room is I may say, I'll take the simplest approximation that the room is completely stagnant. And I put the particle at someplace in the room, and I'm going to equate the Stokes drag force and I'm to the gravitational force. And I'm going to calculate the settling velocity of that particle based upon the balancing of those two forces, right? That's essentially the simplistic equation here. We can, of course, make this much more complicated if we want, but this articulates the point, right? And that point essentially is that if I were to take here a 4-micron aerosol particle and put it at 1.5 meters and let it go in a stagnant room, it's going to take over an hour for that thing just to fall back down to the surface. This is a somewhat unsettling, I think, number because no room that we've ever been in is stagnant. So what else can you do? So we can take this approach another step further, right? You can try to calculate out the trajectories of a droplet using computational fluid dynamics for more of a representative room situation, right? Where you might actually be able to carry some of the velocities in the room. And so essentially we can think about this as our index here sitting at the star in the center of the room with a 10 meter per second exhalation. And you can look at the trajectories of large droplets. Those are shown in blue for 200 to 200 micron to a millimeter size droplet, the deposition timescales for those. That's, again, that makes sense. That's going to deposit on the timescale before it evaporates. On the left-hand side, you can see a 10 micron particle. It essentially doesn't care, right? It's going to start to evaporate out, and then it's going to be carried by the thermal plumes that occur in that room. So this becomes a much more challenging question, is what do we know about the distribution of particulates in a room, and how can we utilize that information to inform these types of risk models? Okay, so that leads us to some measurements that were made here. These measurements were done in an extremely collaborative project with mechanical engineering with Dave Rothmer and Scott Sanders and Doug Randall. And specifically, this was to look at this question. Our interest in this were to determine the spatial distribution of aerosol particles in a typical classroom, right? That informs us of a lot of things. It informs us of our physical distancing, right? It informs us of what this sort of background or maybe well-mixed aerosol population might be. And it informs us about how fast particles might be lost from the room just through physical processes as they are intercepted by a table here or something along those lines. And finally, they allow us to assess intervention strategies. I'm not going to talk as much about that. That was one of the primary things that the engineering component, the engineering team worked on. And you can see in this picture, essentially, what this project entailed. So at each one of these mannequins, you can see in the back of their head that there is a tube extending into the back of their head. That allows us to either send aerosol out through the mannequin's mouth, or it allows us to put an instrument on the back of that and measure aerosol that's being inhaled into the mannequin itself. You can see this was a strategy to put cloth masks on all of the mannequins to look at some of the transmission effects. That wasn't done on every experiment. You can also see that there's light bulbs in front of these various mannequins. They were moved to different places around. That's because one is, as people in the room, we generate heat, we generate thermal plumes. That changes the way that particulates move in and around. And the other is that the heat that we generate triggers occupancy sensors in a room. So many rooms have variable ventilation. And so you want to mimic the number of people that are in the room to mimic what the ventilation is going to do. Okay, so typical classroom. Room size here is about 1,300 square feet, ceiling height 10 feet or so, gives us a room volume. One of the really interesting parts about this room is that it has a variable ventilation system, okay? And this is a fantastic engineering feat because for the past, probably 5 or 10 years, we've spent a lot of time and energy thinking about making buildings efficient because we spend a tremendous amount of energy on heating and air conditioning. And so this efficiency gets us in this context. But it's a challenge because they're variable, so they have an occupancy limit. And so if you reduce the student density in a room that's designed for 48 students to 16 people, you reduce the ventilation. Okay? Baseline supply airflow here is measured. You can see in the back of this picture, this red and blue look like these little tents. You can take those tents and you can put them right on top of the supply. You can measure how much fresh air comes into the room. You can put them on the return, and you can measure how much air gets exhausted out of the room. That's of course how rooms are balanced to be positive or negative pressure. And in the baseline configuration here, you find here that this room gets about 280 cubic feet per minute. It's about 72% outside air, 28% return. And we'll talk a little bit about why that's important. And you hear this number often about air changes per hour, right? And that's the supply flow divided by the volume of the room, and you normalize the units out. So you'll see these numbers creep up in terms of the context of ventilation. Okay? When the room comes to higher occupancy, you can get the system to go as fast as about 4 air changes per hour. Okay, so what was the experiment? The experiment was essentially to do a controlled release of particulates. We controlled release sodium chloride aerosol particles with a mean diameter of about 2 microns. We carried it in carbon dioxide as a tracer for the gas. We allowed that to exit the mouth of a single mannequin to represent a single index or a single infected person in the room. We distributed a network here of NDIR CO2 sensors. You can see we hung them from the ceiling, and that allows us to look in real time at the CO2 plume as it's moving around the room. And we also have particle sensors that are in various locations around the room, and we have some particle sensors we actually moved through the room to build this map. I want to throw an enormous thank you to Blaise Thompson, who helped us with this project on a really short timeline to get this up and running, and it worked beautifully. Okay, so the first thing we did, of course, is to see, do we understand how rooms behave, right? So you have a controlled release of CO2 to the room, guide your eyes to the left-hand side and the blue lines. That's the low ventilation case. That's 1.3 air changes per hour. We inject CO2 into the room. Of course, it's already on a background level because we live in a world that's above 400 ppm CO2 now. CO2 rises in the room. This is the low ventilation case. It takes a long time to nearly approach steady state. And then we cut the CO2 off and we watch it decay out. If we model this scenario with the air change rates that we have in the system, this should give an e-folding time of about 45 minutes, and it does about that. The right-hand side is what happens when you get the ventilation up to 4. You see the overall concentration in the room is much lower. Of course, that makes sense. You see you approach steady state much faster, and you see the decay from when we turn the CO2 off. It's got an e-fold of about 15 minutes. Visualizing these pictures, I think, is incredibly important because it allows us to think about how ventilation changes the concentrations of things in the room. This is an inert tracer. It also makes us aware of the fact what the room is doing after we've left it, right? So in this situation on the right, maybe I had a class, the class ended, we all leave. That room is decaying out with respect to what's in the room. Okay, so if we look in the near field, here. So now these are the sensors that are in the near field right in front of the source as opposed to those that were on the edge of the room in the more well-mixed region. You see all of this oscillation, right? So we're essentially monitoring the plume of CO2 wafting by each one of these sensors, and the concentration in that near field here is, in the near field region is significantly higher. So this is CO2. I think the reason why we do this is, one, is it allows us an ability to understand the ventilation system with a conserved tracer. Two, is it's an opportunity to actually test and diagnose rooms when we don't have this type of experimentation, because every individual that comes into a room for a class exhales CO2. If we know how many people are in the room and we know an estimate of the percentage of CO2 that they're exhaling, you can use that information as a source. You can measure the approach to steady state. You can measure the decay out afterwards. That's something we're doing currently in some of the rooms in our own building. So of course, the question here is CO2 are not particles, okay? So I'm going to skip here and go right to the particulate measurements. So what we did for the particulates is we took a set of nebulizers, and we took sodium chloride to generate particulates from those. And we put them into this large box to create a constant source. And then we ventilated those particulates out through the mouth of this individual. If we change the salt concentration that's in that source region, we can shift the size distribution around. And our goal was to create a size distribution that looks something like exhaled aerosol during talking. I think we achieved that. You see the size distribution peaks around 2 microns here in diameter. So the question is, what does the actual measurement look like in terms of the spatial distribution here of particulates? Okay. So there's a lot of information content in this, but this is one of the key takeaways of this talk. So before we assess some of the risk. So essentially the question is, how close is close in the low ventilation limit? Okay, so this is the room once it's achieved steady state. Okay, so we've allowed the source to come into the room. We've allowed it to come up to steady state. And we take measurements of the aerosol concentration at various points around the room. I'll say 2 important caveats. The colors inside the circles are where the measurements are. The colors in between the circles are interpolated. We attempt to have high coverage in regions of high variability. If you look underneath the map, you can see where the tables are. The star is the index, so that's where the source is. The concentric rings showcase your 3-foot and your 6-foot radius from that source. You can see the squares here, 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 and here. Those are the supplies, clean air supply heading into the room. The return is a single return down here. So you see a couple things. The first is that, sure, inside here, 3 to 6 feet, maybe extending out a little bit more, the concentration is higher. Okay, now here I'm showing the concentration in the room normalized just to this first point in front of the source. The concentration in the room is highest in this region. You shouldn't be surprised by this, right? This is just showcasing the dilution component. The second, you can see how the plume is actually pushed away from it by this supply. It's pushed this direction. It's actually pushed away by this supply, and it heads toward the return. This is, of course, your eye guides to this. Your eye should also guide to the fact that the background here, or the well-mixed part of the room, has a concentration that's about still 30% of that measured 1 foot in front of the source. This is the question about longer range airborne transmission. This region here, like I said, still 30% of that if you're parked right in front of the source. And that's the concern, okay? So what happens if you can control your ventilation, right? If we can take our ventilation rate from 1 air change per hour to 4. This is the same map. This is the same observations. We've got the index. We have the concentric rings that extend beyond this. You can see the plume here looks somewhat similar, right? The air rate, the ventilation rate that's pushing on this in the various directions is stronger now. But the thing that really draws my attention is now the well-mixed region of the room here, say these dots out here, right? It drops to about 10% of that near the source, okay? And this is at 4 air changes per hour. So as we increase this ventilation rate and you're able to maintain this physical distancing, we get this gain, okay? You can imagine what this picture might look like if you were sitting outside, right? Where you're sitting outside in lawn chairs, you know, spatially distanced from your friends, right? Your ventilation rate there is nearly infinite, right? So this becomes a situation that is much, much lower risk than that of the indoor condition, right? And that's part of the reason why the prevalence of outdoor transmission has been so minimal in the observations to date. One final experiment. What happens if you put a mask on this individual? This is essentially source control, right? As an engineer, you would think about source control as being your primary line of defense if you want to think about mitigating the risk to the environment for some sort of pollutant. You want to control the source, not at the endpoint. So if you try to control at the source and you put a mask on an individual such as this, you see a few things that are really interesting to this. One is you see about a 20 or 30% reduction in particle concentration in this near field region. This is normalized to the no mask case. That's important, right? It's not 100%, but it's something. The second thing you see is that you see that the plume stays closer to the source, right? You no longer have this jet that's coming out of an individual's mouth that has to wait to be essentially broken up by the thermal eddies of the room, right? It's being injected through the sides of the mask, above the mask, right? Your glass is fog, right? It's going up, it's being carried in these directions. So you see that the plume is a little bit more diffuse and it's actually a little bit more contained. That alone is interesting as well. Okay, so this takes us a little bit toward the last part of my talk, where I want to talk about risk, and I want to talk about how we can take these pieces together to try to assess what is inherently a higher risk situation? What is inherently a lower risk situation? And the start of that is this constant conversation about how effective the face coverings or masks that folks are utilizing are in terms of their exhalation filtration efficiency here, or their inhalation filtration efficiency. I would note that the thing we want to look at is not just the material filtration efficiency. You want to look at the total effective efficiency, because that is the part that also quantifies the fit, right? And we know that that's a critical part of this entire puzzle, is how well fit your masks are. There is a lot of information in the literature on this, and unfortunately, this is something where the literature is spread because all of these masks are so different and all of the fits are very different. Here's one example. This is from the no-sew mask from the CDC. This is one you can make without a sewing machine, and this is one that's been tested extensively here by Lindsay Marr at Virginia Tech, a real leader in this field. I advise, if anyone wants to know more about this information and are on Twitter, follow Lindsay Marr. Okay, so inhalation filtration efficiency for this mask. Unfortunately, these scales are a little different. This is 1 to 10 microns. You can see if you were to go lower in size, it's not on this figure, it is in other literature, is that the mask efficiency becomes below 1 micron, becomes pretty poor. This comes down to much less than 20% if you get down toward maybe 500 nanometers. Fortunately, we don't think there's a lot of virus that's down toward 500 nanometers. So inward inhalation at maybe 5 microns or so could be better than 50%. The exhalation component is thought to be even better, right? And that's that component here. At one part, it's weighted by the fact that the particles that are exhaling out of your mouth are going to be larger in size because they're at high humidity. They haven't desiccated yet. And the other is just the fluid dynamics of the jet that's being formed as you exhale, and those large particles actually impinge on even a simple cloth mask. So you see something along these lines. I'm going to take some of these numbers and sort of showcase how they can be used. Okay, so I think starting out in this whole thing as an aerosol physics or atmospheric scientist, what I would have wanted to do was the same thing that I do in an atmospheric chemistry type experiment or a field experiment, is I'd want to do like a particle resolved trajectory type model. I'd want to track particulates as they're being exhausted out into the room. I'd want to know all of the individual terms to be able to do that. And this becomes really challenging because there are pieces of the puzzle that we simply do not know, right? We do not know how many viruses are in an individual aerosol particle as a function of size, right? I talked about where they could be, but that's hard to put in a quantitative model. We don't know things like the dose response curve for SARS-CoV-2, right? So again, it's hard to take this all the way from a source model to a receptor model and calculate a dose response curve that you could calculate a probability of infection. So without this type of information, the community has sort of taken a step back and said, well, we haven't had this information for calculating risk for other types of airborne diseases. So what can we do? And so stepping back, sometimes the easiest thing to do is to come back to the foundation, come back to the fundamentals of what has been done over the past 10, 50 years about these types of questions. And so one of the pioneers in this region was Wells and Wells. This is William and Mildred Wells. We'll collectively call them Wells. And in 1955, they proposed what they call a hypothetical infectious dose unit. Okay, this doesn't mean it's a particle. It means it's a unit. And it's essentially your quantum of infection. It could be multiple particulates. There are lots of things that are sort of swept into this number because they're unknowns. And this unit, this quantum, is the number of these infectious particulates required to eventually infect it in person. Okay? So from this idea, what can be built is an idea of a conditional probability for infection. Right? This is a piece of information we might want to know, right? Is that if you were to enter into a condition, maybe that's a classroom, maybe that's a laboratory, how many infection cases are you going to have per the number of susceptibles or the number of people in the room? Usually assuming that there is just one infected person in the room. I think that's an interesting model to think about because in the context of maybe classes we're going to endeavor into, that is probably what may happen. You might have that limit. Maybe there is one infected person in there. So we can calculate that conditional probability as essentially 1 minus e to the number of infectious quanta you inhale during that event, okay? So essentially, this model is very simplistic, right? And it has some very key assumptions. Number one, it assumes that the respiratory aerosol is instantaneously mixed into the background of a room. We showed from those pictures before is maybe that's not necessarily true, but if we stay out of the 6-foot region, it's pretty close. First is second, it's only really appropriate for these infections that can be modeled with their exponential dose, right? Single large dose equivalent to smaller doses over a long period of time. That may or may not be true, but this is at least a model we can start from. The final one is this is probabilistic, right? So it works best if we have large populations, right? If you have a class of hundreds of people, or you have an event with hundreds of people to be able to get this out. This is hard if you have 5 susceptibles. Okay, so the key things you want to know if this model is to be utilized is how do we determine the parameters that impact n, right? This average number of infectious quanta. Okay, so this is my only slide with equations on it, and it is fully annotated here. So the idea here is, on average, how many of these quanta of infectious particulates would you inhale? This is a steady state model. So this value of n, right? This is going to be a function of, or product of 3 things, right? It's going to be a product of the average concentration of the quanta that are in the room. That we need to know about. That's what we'll talk about here next. It's going to be a function of your volumetric breathing rate, right? If you have these particulates in the room, how much air are you bringing into your lung system, and essentially how many of those particulates are depositing when you're bringing them in. And the third component is essentially how long are you there, right? What's the duration, right? This is a dose that you're taking in. You can weight that by essentially how good the masks are that people might be wearing for your inhalation. Right? So you can weight this. If you have a fully effective mask that's taking out all the particulates, this number goes down. So the large number in here that's uncertain or that we want to pin down here is the average number of or concentration of the quanta in the room. This is essentially your steady state equation that comes from this. It carries lots of variables, right? The things that we're most interested in. The most uncertain number in here that we'll come back to is this lowercase q. This is the emission rate from an infected individual. So this is essentially carries the packet of information that we didn't really know, right? How many particles are being emitted, what size of those particles are being emitted, right? And how many of those particles have a virus. If we knew each one of those things discretely, we could package this back up. We don't know that. That's why we're using this type of model. The volume of the room, and then the total first order loss rate. So this is your ventilation term, right? That's how you get them out of the room. You vent them out back through your HVAC system. The clean air delivery rate, perhaps you have an air cleaner that you put in the room. Deposition of surfaces, or the virus deactivation itself, right? It doesn't live forever in an aerosol particle. So if you can solve this type of equation, right, then we can get an idea of what the probability of infection actually depends on, okay? So I highlight in green here the key control parameters. These are things, if I look at this equation, that we can control, right? These are things that we can make policies about that allow us to reduce risk. So what can we control? We can control mask efficiency, essentially by having strict adherence to mask policies, right? And having people wear high quality masks. We can control some of the first order loss rates, ventilation, clean air delivery. Those are things that could be controlled. To some extent, we can control time duration of an event, right? You don't need to linger in places for an extended period of time. Some events you can't. Those are things we can control. In red, I would say these are the things that are uncertain. That's what makes this model perhaps not completely accurate, but useful. The things that are uncertain is how good the mask is, for example, of the students that might be in your class if you're an instructor. How good is the mask of your friends that are sitting at the table with you, while you're eating? That's an uncertain thing. The biggest uncertainty here is the emission rate, the quantum emission rate for an infected individual. And that depends on activity, singing, breathing, talking, or whatnot. So these are the uncertain terms. I would say the inhalation filtration efficiency and exhalation filtration efficiency are things that we can assess. Those are easier to measure, as is some of the first order loss terms. This quantum emission rate is something that's very hard to get in an early phase of a pandemic. So how was that done? So this number, there actually is a number for this value of Q, and it essentially is derived from this Wells-Riley equation. Essentially, it's derived by looking at various case studies in which you know the probability of infection. You know the number of cases divided by the number of susceptibles. And from that value, for example, here's one case for the Skagit Valley coral super spreading event, where that attack rate was around 87%. So from that, you can back calculate, if you know all of the ventilation conditions, what that emission rate must have been to support that. Gets you a value that's around 1,000 quanta per hour. This is for singing, right? This is not for talking, and this is not for breathing, and this is not while wearing masks. So I want to take these numbers in my last 5 minutes here and put this all sort of in context about what do we know about places where there have been outbreaks versus places that we may frequent in this type of model framework. Okay. So this is a little bit of a busy model output that I put together here. The x-axis here is your clean air ventilation rate, essentially your air changes per hour. So I guess it's technically not a ventilation rate, but it's clean air air changes per hour. That's a number you hear a lot about. You've heard that throughout the conversations in the forums here, that chemistry building is 6 air changes per hour, things like that. On the y-axis here, I have duration of event. Okay, so we all know our duration of events. And in many cases, we do know the air changes per hour for some of the buildings that we're in. The color is the conditional infection probability. So essentially, that's the number of cases divided by the number of susceptibles. This star that I put here is essentially what had to happen to be able to get 87%, right? What had to happen is that the ventilation in this system was extremely low. This was about, I think they estimated this around 0.5 air changes per hour. This was a long duration event. It was almost 2.5 hours. People were singing. They're speaking very, very loudly. They're singing, right? And there are no masks. This is the type of event that you continue to see these types of outbreaks. And if we were to take the restaurant scenario, if you were to take the call center scenario, they live in this upper left-hand corner. The question I think that we want to come back to, sort of as we close, is if we were to look at a model like this, what spaces do we visit in this framework? We all know in my entry slide, this is the crowded bar, right? At the crowded bar, you might go and hang out for 3 hours. A lot of these bars or small restaurants may be not very well ventilated, or you just don't know. A lot of those spaces, folks are not wearing masks. That's where we started to see the numbers climb, okay? The engineering classroom that we were in, that would live down here. If you were to say a 50-minute class in the engineering classroom, this would still be to say that the infected individual in that classroom was singing, right? Probably not happening, and probably not that there's somebody in your class that's singing without a mask, but that's where you'd have to live. Okay, so if we take this picture and we scale it to where the environments we may find ourselves, like in a lecture hall, in a laboratory, and we think about it in the context of folks wearing masks and maybe talking but not yelling and not screaming, where do we find ourselves? These are a few snapshots from this model. This is the same y-axis and x-axis for both of these figures. The color that we put on here is no longer up to 1, right? The color now here is up to 8%. Okay? So if you're in an environment here, assuming that the state of the science that we have for this, for a lab class or a lecture class, right? You're finding yourself in this conditional probability with no mask and a value of around 6%. We go to a lecture component here at 6 air changes per hour. Maybe you're down here all the way down, to 2%, right? If we have people wear bad masks, or just regular masks, they're 20% or so, I would say that's really a lower limit on many of the masks that we have. You can see the reduction in these numbers, right? You're weighting essentially the exhalation number. So say there's 100 particles, weight it down to 80, and then weight the 80 down another 20%, right? So you see that reduction. Similar for the lecture, okay? So as we bring this sort of to the conclusion here, you can start to ask yourself sort of where do you live in this conditional infection probability world for the events that you are frequenting, right? And what is that level of risk that is appropriate, right? And that's going to be a decision that various people are going to make in different ways. For example, if you're up here and you're in a lab, and say you're in that scenario where you say, you know, I'm really concerned about this, 4%, I do not going to tolerate a number like that. I want to be cautious in saying that this is a model that has a lot of uncertainty already cooked into it, but essentially say you're in the situation of saying, I want to do the best that I possibly can in this environment. The best that you possibly can do in that environment, this is here a map here for 6 air changes per hour, would be to think about taking your mask here and saying, can I make my mask as efficient as possible? And this is no assumption on everyone else in the room. They're all wearing 20% efficient masks. You're maintaining physical distancing, no fomite transmission, 6 air changes per hour. Say, I don't want to be here. I want to be all the way over here. How do I get there? And this is one of my parting slides, is that there actually is a way you can get there that is actually surprisingly simple. This is an innovation that came from Scott Sanders, Leonard Rogers, Dave Rothamer in engineering. And essentially, they were looking for ways to better fit the masks that they had. And we all know that it comes down to the fit of the mask to the face. And the nose piece on some masks works. Sometimes it doesn't. It just kind of flies out, right? And you breathe and your glasses get fogged. You breathe and you exhale out the sides. A very simple thing that was developed here is a mask fitter. And I've got the link here. It's about $2 in parts. You can make it. There are a couple other mask fitters that are online that you can buy. If you really want to take your filtration efficiency to the best you possibly can, Scott Sanders passed the N95 test with a common disposable mask here using a mask fitter. It works actually surprisingly well. I'll leave the link here for folks that might be interested in something like that. You can get that from the makerspace component. Okay, so I'll part with one slide here about how do we relate this back to the spaces that we might be in. And I'll say that we're fortunate for many different reasons. One, we're fortunate because the ventilation in our buildings are quite good. Ventilation is on average 6 air changes per hour. I want to thank Bob McMahon and Jeff Nielsen for providing so much detailed information on those types of numbers. Majority of the rooms are 100% outside air. That can sometimes be unfortunate when there is a construction vehicle parked next to the air intake, because you know it and we can measure it, right? The carbon monoxide measurements we can measure right outside and right in my office, and they're the same, right? So there's great outside air delivery to the space. There are some select spaces that use return air, which means the air that is exhausted out of the space gets sent through filtration and returned back into the space. Bob McMahon was actually able to go on a mission and find out what those filtration units were and find out what the rating were for those filtration units. Finds out that they're greater than MERV 13, they're MERV 14. If you look on the left-hand slide here of the efficiency of those filters as a function of size, and you guide yourself to the line that says 14, and you look at, say, a 1 micron particle, you can convince yourself quite easily that that return air that's coming back into the room that's sent through this filtration unit will have effectively filtered out those 1 micron particles. Okay, so sort of in conclusion here, the takeaways from this is that, of course, keeping your physical distancing makes a tremendous amount of sense. Wearing your mask makes a tremendous amount of sense, even if they're not 100% efficient. It still gets you that fractional reduction that you get. Limiting your duration in spaces when you can makes a lot of sense. I'll part with one figure here. This is the question that's been on a lot of our minds, and it's a question I think that we're still working to figure out. And that's essentially is how close is close when you're sitting outside, right? Many of us have spent a lot of time sitting outside, moving our social conversations to being outside. And there are lots of questions about whether or not 6 feet, 8 feet, 10 feet, we should place our lawn chairs. And this is something that Stephanie Richards and Joe Gord are going to try to figure out using CO2 tracers to figure out where the CO2 moves as it comes in and around you in these plumes. Okay, so I'll end there. These are some of the acknowledgements. I owe a tremendous amount to Joe and Stephanie and to Gordon Novak, who worked on the setup of this experiment, Blaise Thompson for building many of these NDIR CO2 sensors on this distributed network, Bob McMahon and Jeff Nielsen for all of their input on building and building specific questions. I know very little about the details of our own building, and Bob and Jeff know a tremendous amount of the details of our own building. and to mechanical engineering, Dave and Scott and Doug, who have worked on this project in a collaboration. And finally to Johnson Controls, who's funded the idea of indoor to outdoor air quality and is excited about working with us in moving this pathway forward.